Hi, welcome all to the OneAPI Essentials workshop. As Amit introduced, my name is Praveen, and along with me is Rakshit Krishnappa. We are developer evangelist at Intel, and in this in this session, we'll be covering the OneAPI Essentials workshop, and let's see what the agenda is. So I'll be covering the first two portions of the OneAPI, which is the introduction to OneAPI and the DPC++ program structure, and Rakshit will be covering the other new features like the unified shared memory subgroups and the DPC++ library. So let's look at the agenda first. I'll be introducing you to the OneAPI. I'll introduce to Intel DevCloud. Then we'll do some hands-on training on the Jupyter notebooks on the DevCloud. We'll do some introduction on the data parallel C++ language. We'll talk about some of the SYCL fundamental classes. And also we'll see how we do a device offloading and also create custom device selectors. And we also finally talk about the synchronization mechanisms in a DPC++ application. So we'll be doing multiple hands-on sessions in this while we do the slides. So I'll also help you onboard to the DevCloud in the following slides. And the learning objectives, we explain how OneAPI can solve the challenges of programming in a heterogeneous world. How to use the OneAPI solutions to enable the workflows. How we can actually use the Intel DevCloud, and how we can actually experiment with all these OneAPI tools. We'll understand the data parallel C++ language and the programming model and structure. We'll talk about the basic SYCL fundamental classes, and we'll talk about the device selection and how to offload the work to different kernel to different devices. And we'll understand various ways to synchronize data between host and device in a DPC++ application. And we'll do some hands-on applications, DPC+ applications on the Intel DevCloud. So let's get started with OneAPI. So it was recognized that today each kind of data-centric hardware typically needs to be programmed uniquely, and there are different languages, different libraries. They're all unique, and it requires maintaining a whole bunch of different code bases and libraries. And also with this inconsistent tool support, it also causes developers to have to learn a whole bunch of different programming languages, paradigms, and maybe they were stronger in some and may not be in others, and it's just a challenge, right? So that means developing software for each platform requires a separate investment, and with a little ability to reuse the work to target different types of architectures. So what is the solution? So the solution is OneAPI. And the goal of this project is to deliver a unified software development environment across CPU, GPUs, FPGAs, and different other architectures, accelerator architectures. And OneAPI is a industry initiative. What you'll see today are the Intel implementations of this industry initiative, but it's very much an open industry initiative. You can do your own pull request, can make all the change suggestions. It's very much a wide open effort that we hope many choose to adopt. And the goal is to deliver a unified language and a set of libraries that provide full native code performance across a range of hardwares, different hardware accelerator architectures like the CPUs, GPUs, the FPGAs, AI accelerators, and any other accelerators that may come into existence in future. So OneAPI is foundational programming stack, and it's actually it's used to, as mentioned, right? It's it's used to target uh, target your workload to different kinds of architectures. So let's go to the next slide. And as discussed before, right, OneAPI is being built to simplify development across multiple type of pros accelerators, and it's standard based on we also open specification to enable the broad ecosystem adoption and innovation. So let's see what actually included in the OneAPI open specification. So one thing is the direct programming, and it got an open unified language called the data parallel C++, and there's API based programming um, with a set of performance libraries for expressing parallelism and delivering native high level language performance for all supported platforms. Most of these OneAPI libraries are uh, open source to encourage collaboration and help build the new features and extensions. And also to talk about the low-level interface to hardware, OneAPI, it's called OneAPI 0 level. And together, these components allow other companies, to build their own implementations of OneAPI. So you can actually visit oneapi.com to get more details. Also there is an open call for feedback in there. So please feel free to visit oneapi.com to get more details on that. With that, let's look at what is actually in the OneAPI toolkits. Now, this is a whole program. It's currently in beta right now. We are almost at beta 9 release, and we release it in monthly cadence. So it's under heavy development, and we're planning for the it releases the monthly cadence, and so what you'll see here is we got a base kit, which is our core set of high performance tools. Basically, that's where you actually get started with one API based toolkit. And also, in addition, we also have a HPC toolkit and IoT toolkits, a deep learning toolkit, and then a rendering toolkit. So we're going to focus mostly the base toolkit in this current session, but just for information, there is a core OneAPI the base toolkit, right? Which contain component used by broadest range of developers. So add-on toolkits targeting specific developer workloads are that built on the core on this core toolkit. Each toolkit also includes OneAPI components and complementary OneAPI ecosystem components. For example, the OpenMP, MPI, and Fortran are important parts of the HPC toolkit. Toolkits are also provided via ready-to-go containers and all the customizable installers that support to get fast, reliable, and configuration at startup. So let's look at what's actually in the OneAPI based toolkits. And we got you can see we got a lot of libraries like the communications library, the data analytics library, and the DPC++ compilers in the the DPC++ compiler library. The DPC+ compiler library is to compile and optimize the DPC++ code for the CPUs, GPUs, and FPGA target architectures. And also, if you are familiar with previous Intel libraries like the thread building blocks, Intel TBB, which we call, and these are also used to simplify the parallelism with advanced threading and memory management template libraries. And in addition to that, there is the interdistribution of Python, um, which is a great data science toolkit, which contains a lot of familiar things. And this is just kind of list chain of a list to give you guys an idea of what is contained inside of the toolkit. Uh, so just to something to point out, if you want to do like MPI or Fortran, you definitely need to add the HPC toolkit in addition to the base toolkit. What's also included is a math kernel library to accelerate math processing routines, including the matrix algebra, fast Fourier transforms, vector maths, etc. Right. And the last section, right, we see the profiling tools, like the Intel vTune profiler. It's used to find and optimize the performance bottlenecks across CPU, GPU, and FPGA systems. Um, Also, the Intel enhanced GDB to enable the deep system-wide debug of DPC++, C, C++, and Fortran code. Also, Intel Advisor, which is got tools like Offload Advisor and Roofline Analysis, where use Offload Advisor to identify what parts of your code can take advantage if you actually send it to a device for parallel processing, or where you can actually offload. So it identifies the best parts of the code that you can offload to a device. So this is just in a nutshell. So let's also look very briefly on what's included in the HPC toolkit and how it complements the base toolkit. So as seen, right, and OneAPI based toolkit includes tools like Intel compilers, like the DPC++ compiler, vTune amplifier advisor, and debugger, right? So the HPC toolkit add-on HPC toolkit add-on will get you access to OpenMP compilers with offload capabilities, and the memory and thread debugger tools, the Intel Inspector tool, the cluster tool, and libraries like the Intel MPI library, Intel Trace Analyzer, and the collector tools, etc. So let's look at the workflow. So first of all, right, so as I was talking about the direct programming, which uses DPC++ and the API-based programming before, right? So easiest way is get started is to build upon a framework or library that is powered by OneAPI, or actually we'll explore in this slide what is needed to accelerate the direct programming. Uh, right. So the top box shows there are many languages of choice for direct programming. So this lets you leverage your existing software investment in C++, Fortran, C, OpenCL, and CUDA code. So if you have an existing CUDA code, you can use the Intel DPC++ compatibility tool to perform a one-time migration to data parallel C++. The compatibility tool automates most migration, but there is still manual work involved. Uh, when you're creating the kernel style data parallel C++. So accelerated code can be written in either a kernel or a directive-based style, right? So existing CUDA code, as mentioned, we can use the compatibility tool to migrate. Existing Fortran code can use a directive style based on OpenMP, and existing C++ code can choose either of these options. And existing OpenCL applications can either remain in the OpenCL language or migrate to data parallel C++. So
Whatever,
once we, sorry?
What about MPI?
What is? Can you please repeat the question?
How the MPI will migrate to the new interfaces?
MPI?
Yeah. I mean,
Uh,
I didn't see the MPI option here, so that's why I was just asking.
yeah. So it's part of MVC MPI. It's part of the base toolkit, right? And it can either use DPC or the directory style. The other. You can use the OpenMP style of doing things. So either option. It's
Okay.
all right. So once the implemented, the code can be profiled and optimized using the Intel VTune profiler. Um, so it's an iterative loop. So first you use the advisor to identify uh, the most profitable loops in your code, and then once you write a DPC++ application, finally you'll use the Intel VTune profiler uh, in the tuning phase. So in reality, there's overlap, and both tools may be used during each phase. So let's talk about the data parallel C++. So it's a high-level language designed for data parallel programming, and it's actually based on C++ ISO standards, the standard C++ ISO standards. And we also take advantage of the existing Kronos SYCL standard, which already has got the data parallelism and the heterogeneous computing support in there. On top of it, we have also added some community extensions, which are called unified shared memory and the subgroups, which will be the second part of this session. Um, and so these make use of some advanced hardware capabilities and also to simplify the programming language. Right. So in a nutshell, what is data parallel C++? It's mainly pure C++ plus SYCL, which has got heterogeneous computing support, plus some community extensions. It's based on modern C++, and it also incorporates SYCL for heterogeneous programming. So what about the extensions that we just talked before? So it's mainly for two purposes. One is to enhance productivity, and we try to simplify the language um, to make existing C++ developer just come in and try out, start immediately with the heterogeneous computing. And the second advantage is mainly for performance reasons, to do with the hardware specific features. And to reiterate, this is a community project, and you can actually submit the PR or change request, whatever you plan to. So in this slide, we'll talk about some of the requirements for heterogeneous computing and what are the, what actually involved in a heterogeneous system, right? So first is we talk about the platform model. So in this platform model, right, we got a host and a device that we need to identify to actually offload the work we want to send it for parallel, right? And how are these control and execution handled, which is called the execution model? So we'll be using some of the constructs which like queues, buffers, and accessors. So we'll use a queue to submit the command. We'll be talking about basic secret classes in the upcoming slides. And the third thing is the memory model. How is the data structured and communicated? So how using different types of SYCL objects like the buffers, and also the unified shared memory that will be covered in the later part. Finally, we'll also talk about the kernel model, how we are actually executing that code on the device. So what type of are we using the ND range? What type of work items is it? How are we passing the parallel function? right? So that's the execution model. So these are the most, the four major parts of a heterogeneous system, and that's how we start writing, the basics of a DPC++ application once we understand this. So let's start with the Hello World DPC++ program, right? So this program is, based on unified shared memory model. If you look at that, it looks like a simple C++ code, right? It says main important thing is it's a single source. So you got the host code and the accelerated code in the same source file, right? And we also get introduced to some of the constructs, library constructs like queue. If you see the queue, which we use for the targeting of work to a device, and we use malloc shade, which is used for data management in a DPC++ application. And we also use a parallel for function where we are passing in the range and the ID of that, of that particular iteration space. And we'll simply, just doing a simple allocation of data on the device side. This is the actual kernel. The data of I is the actual kernel we are offloading to a device. And then, we just come back and the results are copied back to that host, and we just display this. This is a very basic hello world. We'll run this actually in the DevCloud, and we'll see more advanced programs. But at least, we just will get introduced to a basic hello DPC++ program, and we get introduced to using of queue, the parallel for other important stuff that's required to write a DPC++ program. We'll also, as I was talking briefly about the vTune profiler, right? So as discussed, right, the OneAPI based toolkit comes with the Intel vTune profiler, and it is actually used to analyze DPC++ code and to find and optimize performance bottlenecks across CPU, GPU, other architectures. It supports popular programming languages like C++, DPC++, Fortran, Python, uh, Java, etc. It's actually one of the popular tools for profiling, and the current production version is widely used. So the next thing is the Intel Advisor. We also touch a little bit on that. So Intel Advisor, it actually gives the recommendation to make the best design and optimization decisions. So it helps determine if your code would benefit from offloading to accelerator even before you have the hardware. So as I was talking about, so we got the offload advisor, the roofline analysis, right? The if you use the offload advisor, it can help you identify the most performant loops in your code that you can take advantage of. It will tell you like these are the most performant loops that you can offload to device to get the best possible performance. So, and the roofline analysis, it helps in optimizing the CPU and the GPU code for memory and compute. There are other things like the vectorization optimization, to enable more vector parallelism and improve its efficiency. Right, but the important things to consider here are the offload advisor and the roofline analysis. So now that we talked about the basics of OneAPI toolkit, and so we'll see what is Intel DevCloud, and how we set up the Intel DevCloud, and we'll also look into the actual Jupyter environment that most of our workshop exercises are currently in. So what is Intel DevCloud? As we have seen, right, we got all these OneAPI toolkits, which got lots of software to install. The base toolkit itself is about 15 gigabytes, and HPC toolkit adds about a couple of gigabytes more, and it gets, others get larger and larger here, right? But to help you out, and help everyone out to experience with OneAPI with the least amount of resistance. We've got the Intel DevCloud. The DevCloud, is our development sandbox that allows you to test and run workloads across CPUs, GPUs, FPGAs. So also what's also great about is you log in, you actually just register, you get an account pretty fast, like in a minute, like you get an account, and you have zero software to install. All you need is a SSH login, or you can actually connect via HTTPS using our Jupyter environment, which I'll be showing you shortly. So it's really the very fast way to start coding. You can try all the toolkits and compilers and performance libraries, and also you get like 120 days of free access. And if you got a good project, you can just talk about us, and potentially we can extend that access. So the key points here, right? There are no downloads, no hardware, no installation. Just immediately get going and start programming with OneAPI. So we'll also see what's actually in the DevCloud. So we got a whole bunch, right? It's hundreds of Xeon scalable processors, usually high clock speed, about 192 gigabytes of RAM, and we also got around 10 FPGAs, probably, right? Also more than 70 nodes of Gen 9 graphics, so that you can test on the Intel GPUs. You can also get 228 gigabytes of file storage, which is mapped to a file storage system. This whole thing uses a queue system, which we'll show you shortly. You can actually request access by just going to software.intel.com and DevCloud. Software.intel.com/devcloud/OneAPI. As mentioned, you can sign up for DevCloud for OneAPI, and it is below location. You can just go to software, Intel Software, or either go to the previous website or this website, and you can sign up for the DevCloud, and you can just open a Jupyter Lab notebook and directly start working with the OneAPI Essentials workshops. So this is just the process, right? You go and give your registration details, and it will take you to the screen where you need to read and accept the terms and conditions. And once you are through that, you'll have the second screen, which shows the different types of connection options that you can connect to. And once you click on that, the current way of doing is using the Jupyter Lab, as I mentioned. Either you can actually use SSH too, but in this lab, we'll be doing with the Jupyter Lab. So you click on one-click login, and you'll see the follow-up screen with launching the server, right? And finally, we are up and running with the DevCloud, where you got the option to launch a terminal, like on a regular Linux machine, right? You got the terminal and you can start working on that. And also you can access the Jupyter notebooks. Let me actually show you, the DevCloud process, right? Let me share my screen. I hope you can see my screen here. This is the Intel DevCloud. So as I mentioned, right? So you got the option to click here, and you click on one-click login, and you will see the terminal, and click on the terminal here. And this is how you can download the OneAPI workshop series. So you can actually type in /data OneAPI _workshop, get Jupyter Notebooks.sh. Hey Rakshit, if you got a chance to paste this command somewhere in the chat window so that attendees can copy the command. So you can just run the command. Right, and you'll have the OneAPI Essential series downloaded to your local onto your local DevCloud account. And you can click on the welcome.inb IP notebook file. You can see the different modules of this. We'll be covering till the we'll be covering these 1, 2, 3, 4, and 7 modules in this workshop. So this is the basics of how you actually register and get onto the DevCloud and immediately start working with the OneAPI and start writing your applications on the DevCloud. Right. Also, some of the things to note, right? Like actually, let me go back to the slides again. So till now I just showed you how you can get access to the workshop material onto your local DevCloud account, right? And now I also shown you the welcome.ipynb, which is a notebook file with and these are the different types of notebooks. The OneAPI Essential series notebooks we got on the DevCloud, and I showed you the welcome.ipynb, right, where we got 7 modules, and these are some of the basics of, like you got the program structure, the intro to OneAPI, then the unified shared memory, the subgroups. We talk about the advisor, the roofline analysis, and the DPC++ library. It's a it's a lot of training. You can feel free to download and go through that. We'll actually walk you through some of the samples shortly. And also to note, is how DevCloud actually you can submit a job to DevCloud. So we use a mechanism called QSub, which is actually, it submits the job. You submit from your login node, you submit the job to the actual, compute node on the DevCloud. So using a QSub command, you give a QSub and following with a script file that actually compiles your program. And this actually submits the job to the DevCloud, and you'll get the results back after 20 to 30 seconds. And we'll also show you that. So you can also check on the status of your jobs. These are just practices on the DevCloud. So you can just use QStat that displays the current running jobs. You can use QDEL if you want to delete any pending job. And also there is a way you can actually interact. I was talking about the login node and the compute nodes on the DevCloud, right? So if you want to request a GPU node or FPG node, there's a separate command like, qsub-i -l. So actually, let me try it on the dev. Let me try it. Right, I can actually log in. Let me log into the DevCloud again, and so let's say I type in clinfo-l here. It says I'm in the login node, so I got a emulation device and a Intel CPU here, right? So let's say I want a GPU node. I just say qsub-i, and actually now I'm actually logged into a GPU node. So if I say clinfo-l, right? So if you see, I got access to the Intel Gen 9 graphics. So actually, you can interact to directly, write your program and test for any Intel specific or any device you want on the DevCloud. You can just exit out of it and come back. As I was showing QStat, it shows what are the pending jobs, right? There are no jobs pending currently. So these are the things, some of the best practices on the DevCloud, you can do. So I think the next part, right, is we'll do a simple hands-on session on the DevCloud, which is introduction to OneAPI, and we have seen a hello world. Let's run the hello world here, right? So all the topics that we talked, right, all the introduction, it's everything very clearly detailed in this particular notebook. So if you click on the, let's say you come here, right, and click on the welcome.ipynb, and so you can actually click on module 1, right? And this is the intro to OneAPI. I've already talked about all these. So you can actually read this, like a book, and everything is clearly detailed in these notebooks, along with the code snippets that we were showing in the slides. So let's run the hello world here, right? Simple hello world. So it's very important to note that these all cells are all sequential. So only if you make changes, the next cell will get reflected, right? So let's say I want to change the code here, right? I need to change, let's say I want to change the code here. Once I change the code, I need to make sure I run this cell, and only that I'll get the information that this being written, right? Uh, so any change you make to, let's say I want to multiply, it's currently multiplying by 2, right, on the device side. So let's say I want to change it to 3. Until unless I run the cell and override this, I can't, this is not reflected. So just make sure you always click this triangle button to run a cell, right? Once this is saved, I was talking about the queue sub, right? So that queue sub is wrapped in a queue. That's the wrapper we already provided. In each of the modules, will see a queue wrapper, which is actually doing a queue sub command for you guys. So, just to make it easy for, directly, you just need to create a simple script files like this, right? This simple.hsh. So you'll just use a compilation command and run it. That's how your script file should be. And let's go and run this, right? You click on that cell and run that, and DevCloud, you submit the job, and you should wait for a little bit of 20 to 30 seconds. Generally, sometimes it can be much faster based upon the load on the DevCloud, but you should see the results back pretty soon. And I already talked about the hello world, right? It's basics, right? We're just creating a queue, and we just initialize the data from 0 to 15, and we are multiplying each of the element by 3 on the device side. So you should see 45 is the result, 0 to 45. So this is computed on the device. So this is a very basic DPC++ hello world program. And so we talked about all these things. Let's actually do a simple lab exercise here, right? And in this exercise, what we'll do is we'll just add 2 elements of 2 vectors on the, and we'll send it to a device for computation. So it's very simple. There are some steps clearly mentioned, right? So the first step is just inspect. We got a vector, we got an array element with 2 elements, 10 and 10, right? So we are adding another input, vector 2, right? We just uncomment that, and then third step, right? Uncomment the following line. We just uncomment that to just display the elements of vector 2. So what we did is we created a new vector to add this to the previous vector, right? And we're creating a buffer. So that's what I was talking about, right? We'll talk about more about buffers and access, but at least for this lab access, we'll just see buffers and accessors are the way of creating, the sharing the data between host and the device in a SYCL application, right? So we created the buffers for vector 1, and step 4, we are actually creating a buffer for vector 2, And then we are using the queue.submit, right? We are using queue, which we are submitting, and we created accessors. Accessors are the uh, access are the only way that you can actually access whatever the data is inside a buffer, right? So we'll talk about buffers and access as I mentioned in the upcoming slides. So but we are creating buff accessor for each buffer. So we're creating accessor for vector 1, and we created the accessor for vector 2. So we just keep in mind, if you have got a read only, this is a read only accessor, and if it's by default it's a read write accessor. You don't have anything specified here, it's a read write accessor. So we got read write accessor and a read only accessor, right? So the elements are read from vector 1 and written back to vector 1. And step 5 we uncomment that. Step 6, we just comment this line and uncomment the next line, which we are adding the two vectors together. And yeah, this is the code that actually is offloaded to a device. So at the device here, we are using a queue, right? And by default, we are leaving it as default so that the system selects the best available device here. And once we make the changes, we'll just run the code and submit that. Just remember that I ran this cell to update this particular code, and then I ran the cell again. We should see a simple addition of these two vectors. You also can, clearly it's all detailed in this paragraph, the lab exercise here. You can actually go through all the stuff, whatever I talked about, and get more understanding. So simply, it's offloaded to Intel Gen 9 graphics. We got two vectors, 10 and 20, and these are added on the device side. So these are the basics. So let's go more in detail into the SYCL classes so that you'll have a clear understanding, and we can do more lab exercises on this. So let me stop this screen here and let me go back to my slides. So we got here. So we did the hands-on simple exercise, right? And we did the vector add, right? So let's talk about some of the basics of SYCL classes. So the first thing we talk about is the device class. So in the starting of the session, I was talking about the platform model, where you need to actually identify the devices that are connected to your system that you can actually offload to, right? So, and also you can actually simply do this by calling a function called, you create a queue and call a function called queue.getDevice, and you get the access to the device, and also you call the getInfo function, right? And you can get lots of information like the name, the vendor, the version of the device that you are connecting to. So this is one of the basic SYCL classes, which is the device class, and there are multiple ways actually you can do a device selection using a queue, and we'll see in the following slides. So the second one is the device selector class. This is the selector class that you actually use to select the, at the runtime, you select a particular device to execute your kernels, right, to actually offload your work to. So for example, you can see there are multiple different types of selectors. One is the default selector, and if you use the default selector, the system selects the best available device for you. Or you can actually, if you want to actually offload to a GPU, right, you use a GPU selector class, and or a CPU selector class. And once you create a selector class, you actually pass it as a parameter to the queue. Let me actually use pointer options. Yep. So I'm creating a queue, and then I'm passing in the specified selector, right? So that's how actually I can select a particular device. So next is the queue. Queue, shown before, we submit the command groups by using a mechanism called queue, and actually a queue, using the queue, it actually, once you submit the queue and then you set in your command group which will contain the accessors and the data dependence, all the conditions, right? So you create a queue and you submit the work to the queue, and one queue can map to one device, and multiple queues can also be mapped to the same device. So we'll see some examples of the queue and uh, usage of the parallel for function inside a queue function as a command group handler, right? Following slides. So this, you can see this in this slide, right? I got a queue defined here, and so I can have multiple selectors. So particular queue, I can select a CPU selector or a GPU selector, or using a Intel FPGA selector, right? Or there's another option, that you can do is you can actually create a custom selector on your own. Like, you just create a custom selector class and you derive it from the device selector class, and actually you can create your custom logic, to uh, to rank the devices that you want to offload to. So there's a simple lab that will be doing on that. But you can actually, for now, just remember that you can create a custom selector of your own, and actually you can customize how you can offload to a device, to any particular device you want to, a vendor specific device. Specifically, if you want to target a vendor specific device, you can create the custom selector class. So this is the kernel class, and so as I was talking, right? So once you submit the q.submit, and the kernel class, it encapsulates the methods, right, to actually send the parallel, to send the work in the kernel. Actually, we call the work to be offloaded as the kernel. So this kernel class, it encapsulates the methods to send using the parallel for method to offload to a device. So we're using the parallel for function, and we are passing in the range and the ID. So the range is nothing but the complete iteration space of your data elements, and the ID is a single instance of that particular iteration space. So, and if you see A of I is B of I plus C of I, this is the actual kernel, which is, you consider this as a vector addition here, simple vector addition. This is the actual kernel will be offloading to a device, if you see at least in this particular code. So I was showing a simple lab, right, in that we created buffers and accessors. So buffers, these are nothing but, uh, so the host and the device, they got discrete memories, right? So obviously they can share the memory between, those memories can be shared because they are discrete, but how you actually share the data between the device and the host, or the host of the device, right? So this is SYCL provides a mechanism called the buffers and accessors. Buffers are nothing but 1, 2, or 3-dimensional arrays, uh, you know, which actually takes the ownership of the data on the host side, and accessors are the only mechanism to access this buffer data, either on the host side or on the device side. So you create accessors. If you create accessor on the host side, they're called host accessors. On the device side, they're called device accessors. And there are different types of access. But in this purpose, like the main purpose, we create a buffer, we create an accessor on the device side, we access the buffer data, we manipulate with the data, and then we send back the data to the device side. We either create a host accessor on the host side and to retrieve the results back. So this is iteration, and it also helps in creating data dependencies in this SYCL graph. So graph is nothing but you got nodes, and if you see in the upper top part, this is the graph, right? So there are multiple kernels, uh, so and which got dependencies. So the 2 is dependent on finishing of 1, and 4 is dependent on finishing of 2 and 3. So these are data dependencies, right? So the accessors, they create the data dependencies in this SYCL class, and you actually you only work with kernel 4 only when kernel 1 and 2 are complete, and also kernel 3 is complete. So uh, this is one example of what is a data dependency, and how this will be handled. So the main thing to take out of this slide is buffers are the way to share the data between the host and the device, and accessors are the way to access this data, buffer data, and also to create the data dependencies in the SYCL graph. right? So let's do a simple code anatomy here. We create a DPC++ program uh, by simply calling, by simply including the namespace CLs, including the header file SYCL.hpp, and also we use the namespace SYCL to, make it less redundant, the code, right? So we use CL SYCL.hpp and using namespace SYCL. So let's do a simple code anatomy here. So I'm creating a device queue here, right? So you can observe that I'm not passing any selector here, but if you want, you can too. Here I'm leaving it to the system to select the best available device, and the second thing, we got 3 data items, right? And I created buffers for A, B, and C. I created buffer A, buffer B, and buffer C, right? With the range specified. And then I submit the command for execution. So one thing to note here is once you submit the queue, so till here, it's in synchronous mode, and the queue submits and it exits, right? So everything after the queue submits happens in asynchronous mode, and we'll talk about a little bit about that in the following slides. So uh, after we submit the queue, we're creating the accessors to access the buffer data on the device side. So I created accessor A for buffer A, accessor B for buffer B, and accessor C for buffer C, right? So A and B are read-only, and C is a write-only accessor, right? So we are reading from A and B and writing it to C, right? And once we are done with that, then we just call the parallel for function. We call the parallel for function with the range specified, and also the invocation ID I, which is the single item in the iteration space. And finally, we write the kernel, which is the vector addition. C of I is A of I plus B of I, right? So very simple. It's a simple vector addition. So all these kernel invocations are executed in parallel. The kernel is executed, invoked for each element of that particular range, and it has got access to the invocation ID I. Simple program. So once this is done, if you see, this function is out of scope, and the buffer is destructed, and the results are copied back to vector C after the buffer C gets destructed. We'll talk about this buffer destruction synchronization a little bit later, but at least the results are copied back to the host from the device. So this is a very simple DPC++ code anatomy here. And the next slide, we'll talk about the custom device selector. I was talking about that, right? How we create a custom device selector. If you want to actually, let's say, target a vendor specific driver, let's say you want to target a Intel specific GPU, right? So this is how you create a selector. So I created a selector called my device selector, which derives from the device selector class. And I just gave a simple logic, right? So this is an example. So let's say you want to find a Intel Gen 9 GPU, Intel GPU, right? So the logic we give is, if the device is a GPU, and we get the name of the device as, let's say, the specific to vendor, any vendor like Intel, right? You find the device, you give it the highest rating. And if you don't find the device that in that particular vendor specific GPU, then give the rating to any other GPU that you find in that. If you don't find any GPU, then give the least rating to a CPU. So that's the least preferred option, right? So I can just change my logic anyway, whatever you want to. But just an example. So I created an instance of my device selector class, and I'm just passing it to the queue. So it's a very simple way of creating a custom device. We'll be doing a simple lab on this, right? So I was talking about the asynchronous execution, right? In a SYCL application, right? So think this SYCL as, we've got 2 parts. The first is the host code that we have seen, right? Host code, and the second is the graph of the kernel executions. I was talking about the graph, right? I was showing the data dependencies graph. So it's nothing but, the graph got a bunch of nodes, and a node is nothing but, it's a particular action that's being performed, and the most common action being a data parallel device invocation. So the host code submits work to the device, and the kernel executions and the data movements executes asynchronously. So queue submits, I was talking, right? Queue, once you submit a queue, it until then it's all synchronous. It just exits after it submits the queue, and whatever happens inside the device is all asynchronous. And let's see how you can actually synchronize data, right? So in this example, you've seen, I got a queue, I submit the queue, right? And the parallel for function which we submit to the device is all asynchronous in nature. And we created a host accessor actually to synchronize the data. Host accessor is a blocking call. We'll talk about that in the following with the code snippet, but host accessor is a blocking call that actually waits till all the enqueued jobs are finished, and then it finally fetches the results from the device to the host, and then we display the results. So this is a same graph that I was talking about, but it gave more details on that. So I got kernel 1, kernel 2, kernel 3, and kernel 4. And kernel 2 is dependent on finishing of kernel 1. It's accessing the same data A, right? And kernel 4 is dependent on finishing of A and the kernel 1 and 2 and 3. So it requires data from A and B. So the same code is laid out here. So I got a queue.submit, right? The first job, and then I wait here, and then the queue.submit for the second job, which is the kernel 2, right? And then kernel 3 is happening separately, which is independent, and I got a I created accessor for data B, and kernel 4, which is dependent on kernel 3 and the data A, right? So I created two accessors, A and B, and finally, that's how the data control and how you actually create multiple queues and do a uh, control of the data. So this is one of the examples using how you synchronize the data using a host accessor. So it's a very simple example. I got a buffer. I got a vector V which got around 100 elements, and I initialized the value to 10. I created a buffer for that vector, right? And the buffer takes the ownership of the data stored in the vector once you create a buffer, and then and then you submit the queue, right? And this is executed on the device, this particular function. We're just subtracting each element by 2, so the value should be 8, right? But this is the actual kernel that we are offloading to the device. And if you see, I'm creating a host accessor here. Host accessor is nothing but this is the blocking call, which will and will only return after all the enqueued DPC++ kernels that modify the buffer are completed. So this waits till all the synchronous tasks are complete, and the results are copied back from the device to the host, and then we display the results. Similarly, there is another way called the buffer destruction way. So the same thing, right? So I got see the same code, but I'm calling a different function here. I created a queue and I'm calling a different function. And the buffer is created in a separate scope, in a functional scope. And it's the same process. We created an accessor, we sent using HBuffer to a device, we subtracted by 2 uh, on the device side. And this buffer is out of scope after this function ends the scope. So the results are automatically copied to the device. So these are two different ways how you synchronize the data between the host and the device, right? So let's actually go to the DevCloud again, and let's run some of all these examples that we talked about. So now let's go to welcome.ipynb, and I'm clicking on DPC++ program structure. Again, the same thing, all these, whatever we discussed, the device selector, everything is, uh, rate, everything is clearly detailed as per what we discussed, in the particular slides. So let's first start with, the device selector class, a simple class. So this is doing nothing, it just, we are creating a queue, we're creating a GPU selector, and then we're passing a queue and just naming the device. So it's simple program. Let's run this. So most of these, right, you just don't need to change anything except the lab portions. Everything is in good shape. You just make sure that you run the cell and then come back and run the cell again, and this particular build and run section again to get the results back. So let's give it a little bit of time, and so the simple first exercise, right? We select the device Intel Gen 9 graphics. So we're just displaying the device in the first example. Let's go to another example in this. So we already talked about all this code, anatomy, right? So this is the same example I was talking about in the data dependencies. So I got A and B buffers, A and B defined, and so I got different kernels, 1, 2, 3, and 4, right? And you see the graph as talking about before, I was talking about before. Uh, kernel 2 is dependent on kernel 1, and kernel 4 is dependent on finishing off kernel 2 and 3.
You're supposed
So,
to compare in the terminal. I'm still looking at the slide.
oh, sorry, you're looking at the slide?
Yes, you're supposed to switch to your terminal.
Oh, sorry. Thank you. Thanks for, I thought I switched. Okay, let me stop sharing the screen, and sorry for that. And thanks for letting me know on that. Okay, Jupyter Lab.
There is one question also. Is NVIDIA GPU also available?
On the Intel DevCloud, no,
Yeah.
only the Intel Gen 9 as of now are available on the Intel, on the DevCloud.
Yeah.
So hopefully you're seeing my browser now and the DevCloud. So just want to show you the previous sample that I showed. So GPU selector, and we are just displaying the selector here. We ran on the DevCloud, and it's displaying the Intel Gen 9 graphics driver. Right, that's the only example I ran before. The simple selector class, right? So now let's go to the second example, and yeah, this is the data dependency graph I was talking about, which we already talked in the slides, right? The same code snippet, we got it here. So kernel 4 is dependent on finishing of kernel 2 and 3, and kernel 2 is dependent on finishing of kernel 1, right? All these data dependencies, there's a simple code snippet that can actually help you learn the concepts of the data dependencies and how you handle it. So I created a queue. So there are two buffers, A and B, and the kernel one, we just created accessor for A, and this kernel 2 is dependent on finishing of kernel 1, and kernel 3 is independent, so it's working on buffer B, right? And kernel 4 is dependent on A and B. So each has to wait till the other subsequent jobs are finished. And finally, we created a host accessor here. So as I mentioned, it's a blocking call, and we have to read the results from B, right? That's what is the final data that we are adding to. And let's run this code. Just give a little bit of time, and we should get the results back. And we got the results back onto the host. So let's go to the host accessor, right? The same example. We created a host accessor here, and the element is 10. There are 16 elements. We initialize the values to 10, and then we are sending it to the device. Just a simple example, we are subtracting by 2 and created a host accessor to synchronize the data from the device to the host. Let's just run this sample. So we got the results back, all the 16 elements subtracted by 2, and the value is 8. Similarly, there is a buffer destruction example where we got these buffers and created in a separate functional scope, right? And the same thing we are doing. We are initializing by 10, and we are creating a default queue, and we're calling the function DPC++ code. And let's also run this. It's the same thing. Once this function is out of scope, then uh, the data is automatically copied back to the host from the device. Run this, and so I mean, as I mentioned, you can actually go through all these nodes on the Jupyter notebook, right? And you can just easily run through all the examples going through the nodes in the Jupyter notebooks. So we got the results back using the buffer descriptor, the same results. So finally, we'll do a simple lab here, right? It's a multiplication of complex numbers. And these are not standard template library complex numbers class, by the way. So this is a template complex class that was created separately, and we are passing in these complex classes as the buffer objects. So for example, right, I can show you that the main program, I created a vector of the complex2, which is a customized class. We created 2 vectors, which are input vectors, and we created a third vector, which is the output vector that actually computes the multiplication of the complex numbers in each vector, and copy, which will have the output, the multiplied result in this output complex, this output vector. So let's say we got 3 vectors. A fourth one is scalar, which is happening in serial. We are not even sending it to device. We just run it on the CPU side, and we just compare the results. So, but first thing, main important thing, we initialize these values by random. I just created random complex numbers and pushed into the vectors, right? We created, like, let's say the number of elements is 10,000. Yeah, these are 10,000 elements, right? So I got 10,000 elements in each vector, and I initialized the values randomly, and I initialized my output vectors too, which are parallel, right? And then I passed in, a string. I've created different vendor names here, and let's say I want to specifically target Intel specific vendor. So I created a vendor name string called Intel, and I'll also show you the custom device selector class here. This is my custom device selector class, and I'm passing in the vendor name as a parameter here, right? I create a custom device selector and inheriting from the device selector class. And what I'm doing here is, the first step, right? You can follow the steps 1, 2, 3. Everything is in the code. So just follow the steps 1, steps 2, and step 3 to build and run the code. So the first step is I created a custom device select class, and the first step is the logic to offload my work to a Intel GPU. So I'm going to uncomment these lines. And what this is saying is, if my device is a GPU and the vendor name is that's passed by the string, which we are in the main program, we are passing Intel as a vendor name. So if it's Intel GPU, give it the highest priority. If it's any GPU other than Intel, give it the second priority. And if it's a CPU code, if you don't find any GPU, then offload a GPU, which is the third priority. So that's how you can actually change the logic as per what you require to whatever you want to give the highest priority to. And then I'm calling the DPCPP parallel function, right? So in my main program, if you come back down, so I created the custom device selector class, right? And then I'm passing in this particular selector as my parameter to the queue. And then I'm passing this queue to my parallel function. And let's see what's inside the parallel function. I go to the parallel function, and I got these three vectors. 1 and 2 are the inputs, and third is the output, right? So I created the buffers for vector 1 and vector 2. So these are the input buffers. And I created an output buffer, which is the buffer out, right? And then I submit using q.submit. So if you see the queue, we submitted with the custom device selector class. And in this, we are actually creating the command group handlers, which got the accessors and the actual parallel for function. So I created accessor v1 and v2 for buffer, buffer 1 and buffer 2, right? And step 2, right? We uncomment the line for creating an accessor for the output buffer, which will be a write only. So I got a vector buffer out, which we created as a write only vector. And finally, we uncomment the line to call the complex multiplication function that computes the multiplication of the complex numbers. So this is the one. So this is my actual kernel that I am offloading to a device, offloading to that particular device. So what I'm doing is I am assigning the output vector by multiplying the element one of first, all the elements in vector 1 to corresponding element in the vector 2. So we're multiplying the elements in the complex numbers in the vectors, and then we're assigning to the output vector. So this is then we're done modifying the code. We just run the cell, right? Come back and run the code. Let's just give a little bit of time, and this should be done. All right. So if you see, I ran the code on Intel Gen 9. I ran my multiplication, on the Intel Gen 9 HD graphics, and this is the output. So it computed that all the 10,000 elements in each vector, and then the output vectors, we got the results displayed here, right? And the same thing, once we do the parallel, just for sanity check, right? What we'll be doing is compute the same thing in serial, So I'm using a scalar. So what I'm just doing is calling the function directly instead of throwing it to instead of offloading to device, and then we're just comparing these two to make sure it's a sanity check and they're equal. That's it. So it's a simple lab, but it gives all the details of creating a custom device selector class and creating buffers and accessors for each data element. Actually, in this, we are passing a custom class as object to the buffers, and we computed this in parallel. So let me go back and So we're done with the complex number multiplication. So please feel free to go through the lab section on the Jupyter notebooks and try out all the examples that we ran, and to get more conversation and familiarity with the basics of DPC++ program. And just to recap what we did in this particular session, we have seen what is OneAPI and how it solves the challenges of programming in the heterogeneous world. We have seen different workflows and how we take advantage of these OneAPI solutions to enable the workflows. We use the Intel DevCloud we created, we logged into the Intel DevCloud, and we tested the OneAPI tools and libraries. We introduced to the DPC++ language. We got introduced to the DPC++ language and the programming paradigms and models. We discussed about the important classes like the queue, the kernels and stuff, and the DPC++ application. We've seen how we can actually upload a work to a device using different device selector classes. We've seen what are buffers, DPC++ buffers, accessors, what is a command group handler, and what's a kernel, how we are submitting the kernels. And we've done some nice hands-on activities like vector add, simple vector add. We did some synchronizations, how you do the synchronizations, data dependencies, and finally a lab on complex number multiplication using a DPC++ program. With that, we'll use the next 10 minutes. If you got any questions that I can answer here before we take a break and Rakshit comes back with his session on the unified shared memory and subgroups.